Okay, so we are now going to discuss the Dirac delta function. So let me tell you how the Dirac delta function is defined. So Dirac delta function, it's defined as follows. So it's denoted by delta of x minus a, and this is equal to 0 if x is not equal to a. Okay? So it's 0 everywhere except for the single point where x is equal to a. And then the next thing that we say is, if we do an integral from b to c of delta x minus a dx, this is equal to 1 if a lies inside the integration domain. So if a is bigger than b and less than c, this is equal to 1. And of course, it would equal to 0 otherwise, because at least if a is inside the integration domain, we are integrating over a point where the delta function is non-zero. If a is not inside the integration domain, then we're just always integrating over regions where the delta function is 0. And the integral of naught is naught. You don't catch any area under the curve. So that's the definition of the Dirac delta function. This is a bit of a weird thing. It's actually not a function. It's a distribution. So let me put here distribution. And the fact that it's got a different name tells you it's a different thing. It's not a function. There are things you can do with functions that you cannot do with distributions. So let me give you an example. If you square a function, you get a function, and squaring functions is well defined. When you square distributions, that's not a well-defined operation, and you actually have to work to define what you mean by the square of a distribution. Okay? We're not going to need to go into that in any depth, but it does sometimes appear in physics, for example, in the derivation of Fermi's golden rule. But for us, well, we won't need to delve into that. One thing I do want to do, though, is to give you some sort of an idea as to how you should think about this. And to do that, I want to introduce another function. So let's introduce a function. Okay. This function will be centered about the point x is equal to a. And let's give a function that has the following shape. So it's 0 everywhere until we get close to a. Then it goes up, goes along, comes down, and then it's 0 again. And let's make this function in such a way that it has a width of epsilon. So it's non-zero only for this little epsilon width around A, and it has a height of 1 over epsilon. So why did I choose this epsilon, 1 over epsilon? It's so that the area under the curve, this will be equal to the height times the width, which is 1. Just like the delta function. When you integrate over the delta function, you get 1. So the area under the delta function is also 1. But the delta function is only non-zero at one point. So what you should do is, you should take the limit that epsilon goes to 0, and so you get this function becomes very, very skinny, but very, very tall. And in the limit, it's infinitely skinny and infinitely tall. That limit that epsilon goes to 0 gives you the delta function, delta of x minus a. So you should think about it as a very skinny function that's also very tall. Okay, so that should be your intuition for what the delta function is. Now, using nothing more than the definition that we have been given, we are able to do integrals over the delta function. So I would like to illustrate that, okay? And the integral that we're going to do, let's integrate from 0 to 4. This is going to illustrate all of the tricks of delta of x minus 2 multiplied by the f of x dx. And we'll do this integral for any function f of x. Okay, so I'm going to want to use a result. So let me put the result below. And I claim that this equation is true. So the delta of x minus 2 times by f of x is equal to delta of x minus 2 times by the f of 2. Let's check this, okay? So let's first of all, let's do a check. So first of all, consider, I don't know, the case that x is equal to 3. Okay, let's plug in the value of x is equal to 3 and see if this equation is true. Well, we'll have delta of 3 minus 2 times by the f of 3 is equal to the delta of 3 minus 2 times by the f of 2. But the delta of 3 minus 2 is the delta of 1 times the f of 3, which is equal to the delta of 1 times by the f of 2. Now, what we know is delta of x minus a is equal to 0 if x is not equal to a. So if whatever sits inside the argument of the delta function is non-zero, it means the delta function vanishes. So in particular, delta of 1 will be 0. So this equation says 0 times by f of 3 is equal to 0 times by f of 2. Well, that's true. And what I've just done here can be repeated. So this argument is true for any x which is not equal to 2. Okay? So, in fact, this equation that we want to prove, we've already proved it for all values of x not equal to 2. So the only thing we have to do now is we need to check what do we get when x is equal to 2. Okay? So let's plug in x as 2. So delta of x minus 2 becomes delta of 2 minus 2 times by the f of 2 is equal to delta of 2 minus 2 times by the f of 2. So I've just plugged in everywhere I saw an x, I've replaced it by true and by 2, and this is obviously true. So the equation is also true when x is 2. So it's true if x is not 2, and it's true if x is equal to 2, which means this equation is always true. Good. So let's now use this equation. So this is equal to an integral from 0 to 4. And instead of writing delta of x minus 2 times by f of x, I can write this as delta of x minus 2 times by f of 2. But f of 2 is a constant independent of x, so I can pull it out of the integral. So this will be equal to the f of 2 times by the integral from 0 to 4 delta of x minus 2 dx. So now I have to evaluate this integral. This integral sitting over here. But look, the integral from b to c of delta of x minus a dx is 1 if a lies between b and c. Well, here we are integrating from 0 to 4 of delta of x minus 2, and 2 does lie between 0 and 4, so that integral is just equal to 1. 1 times by f of 2 is equal to f of 2. So there we go. We just did the integral, and we did it using nothing more than the definition of the Dirac delta distribution. or direct delta function. Usually you'll write down the answer much more quickly. Once you've had some practice, you'll be able to just look at the integral and write down the answer. Let's just do one more example. And in fact, let me just erase this over here, just to make a little bit of space, because I want you to be able to see the two results. Good. Okay. And what I want to do now is I want to study the integral. I want to study the integral from 0 to 1 of the delta of x minus 2 f of x dx. Well, first step is exactly what we did before. So this is integral from 0 to 1 delta of x minus 2 f of 2 dx. And then f of 2 is again a constant, so we can pull it out of the integral. So this is f of 2, and it's go from 0 to 1 delta of x minus 2 dx. But now we're integrating from 0 to 1 of delta of x minus 2. Well, everywhere that we're integrating, the delta function vanishes. So we're actually in the second condition in the integral. So the integral is just 0. So we just get 0. Okay. So any integral that you want to evaluate, you can evaluate it using the kind of logic that we have used here. I'm going to write down one last formula, and I want you to try to prove this. See if you can prove this. So an integral from, let's say, b to c delta of x minus a f of x dx. This will be equal to the f of a if b is less than a is less than c. So if we've caught the point where the delta function is satisfied, where its argument is 0, and it's equal to 0 otherwise. Okay? I want you to see if you can prove that. If you can prove what's inside this boxed formula on the page, then you have understood the definition of the direct delta function and how to integrate over it.